Assalamu alaikum and good morning. So today we're going to continue with our topic 6, electrochemistry. But even though the topic is called electrochemistry, mostly for your AS syllabus, we are only going to be dealing and looking at oxidation numbers, redox reactions, half equations, and balancing your equations using oxidation number. Okay, so last lesson we've looked at the rules in order to work out your oxidation number or oxidation state. So remember when I introduced these rules to you, it doesn't mean that you have to apply all the 9 rules at the same time when determining your oxidation number. Okay, so it is a case by case scenario, all right? So it depends on what type of molecules or compounds you are looking at. So in your questions in forms, I've already asked you to work out the oxidation number of calcium carbonate. So just check that for calcium carbonate, you should have gotten calcium as +2, carbon as +4, and oxygen as -2. Okay, so I like to break it down into its ions: calcium 2+, CO3 2-. Okay, so calcium is easy to see that it will have an oxidation number as its charge because it is a single monoatomic ion. So that's rule number 3. For H2O2, this is where your rule number 9 comes in, and also rule number 7, where it says hydrogen will always have a charge of +1, except when it is with metal hydrides. Okay, so you have to work around the fact that hydrogen has an oxidation state of +1, oxygen will work out to be -1. Next, for G, N2O, nitrogen will, so nitrogen and oxygen both would usually have a negative charge, where nitrogen is -3, oxygen is -2. Now, if you were to use that oxidation number following its charge, then it doesn't work out because the total, the sum of the oxidation number in N2O has to be 0. And obviously that will not add up to 0. So they are fighting. Nitrogen and oxygen is fighting. Who will win? Who will get priority of the negative oxidation state? Usually, based on rule number 5, the more electronegative atom or element will get the negative oxidation number. So between nitrogen and oxygen, if you still remember your trend in electronegativity, so as you go from left to right, electronegativity increases. So that means oxygen is more electronegative than nitrogen, so oxygen will get its negative oxidation number. Okay, so to work out for nitrogen, you just write this down: 2N, that means 2 atoms of nitrogen, plus oxygen, which is -2, and there's only 1 atom of oxygen in that formula, should equals to 0. So this brings you to rule number 2. The sum must be equals to 0. So if you work it out, -2 will become +2 when you move it to the other side, divided by 2, and will work out to be +1. Right, so that's not the usual oxidation number of nitrogen, but that's not to say that it cannot happen. It is possible. Okay, NaClO4. If you see group 1, group 2 metals, most likely they are going to be an ionic compound. So I would separate them out into into ions, Na+ and ClO4-. Okay, so how do I know this? Because there's only one lot or 1 unit of sodium. So that means the charge of ClO4 has to be -1. Okay, so then this makes it easier. Sodium, based on rule number 3, sodium will follow its charge. Therefore, it's +1. And then we have to work out chlorine and oxygen. So we know that oxygen is more electronegative than chlorine. So we can, if you want, write down oxygen as -2 first, and then you work out when chlorine plus 4 lots of oxygen, the sum should be -1, not 0, because of the charge. Let me see. -1 and the charge here. Okay, so I'm trying to highlight that. And then you just work out your chlorine. It should be positive +7. Okay, so that means your chlorine has an oxidation state or oxidation number of +7. Next, sodium oxide Na2O2. Again, there is a group 1 metal, so I will try to break this down into its ions. Sodium will always be, regardless of what number we have here, sodium will always be +1. Okay, and A plus. And then your oxygen, there's 2 lots of sodium. That means the charge of your oxygen O2 is 2-. So that is an ion. Okay, O2 2- is an ion. So if you're not convinced about this, you just do the reverse. If you bring down, if you bring down the plus and you bring down the 2, so it becomes Na2O2. Okay, so based on rule number 3 again, sodium will be +1. Oxygen, we have to work out 2O is equals to -2. So this is rule number, polyatomic ion, rule number 4. Okay, so you work out your oxygen to be -1. Again, this is not the common oxidation state or the common oxidation number of oxygen. Now you will notice that sometimes these elements don't have its normal or its common oxidation number, and that is fine still. That is nothing wrong with it. Just like transition metals where you can have iron 2+, iron 3+. So that means Fe can have an oxidation number of +1, +2, +3, and etc. Okay, so this works out for your non-metal elements as well. Okay, so you can see from nitrogen and oxygen, they have variable oxidation numbers. Carbon as well is possible. Next, we want to look at chlorine Cl2. This follows rule number 1. All uncombined elements. That means it doesn't combine with other elements, even though there are 2 atoms in there. So the chlorine, each chlorine atom has an oxidation number of 0. P4O10. This one is rule number 2. So that's not an ion because it contains phosphorus and oxygen, which is both non-metals. So when we add between phosphorus and oxygen, you need to give priority to the more electronegative element, and that priority goes to oxygen. So oxygen will be -2. To work out phosphorus, you take 4 units of P plus 10 units of oxygen is equals to 0. Okay, so phosphorus should work out as +5. 20 divided by 4, yeah, +5. Okay. CrCl3, chromium is a transition metal, so we do not know its oxidation number, but from here you can see that this can be broken down into ions because it consists of a metal and a non-metal chlorine. So if I break that down into ions, Cr3 plus, Cl minus. So you can easily see the oxidation number of chromium is +3. Oxidation number of chlorine is -1. Okay. Right, so that's the first part. Continuing the questions. Barium chromate. Okay, so barium is a metal in group 2. So that looks like an ionic compound that I can separate out, Ba2 plus and CrO4 minus. Now, I hope you are able to break up ionic compounds into its ions based on the formula that you are getting. Okay, it is the reverse of doing this. If we want to work out the formula of an ionic compound given the ions, I'm sure all of you have learned this method where you bring the charge down and across. Okay. BaCrO4. Now that is, there's something wrong with this. Sorry, it's not minus. It should be 2 minus. Okay. Otherwise it would, okay, CrO4 2 minus. If I did that, so luckily I checked, then it wouldn't be BaCrO4, it would have been BaCrO4 2. Okay, so again, just to check, if I bring down 2 and if I bring down the 2 plus and the 2 minus, they cancel out to work out as BaCrO4. Okay, so usually ionic compounds are written as their empirical formula. Right, so barium, which is in group 2, based on rule number 3, would be +2. Chromium is a transition metal, and it's not a full formula, it's an ion, so we have to use rule number 4 to work out the oxidation number of chromium. Between chromium and oxygen, oxygen is more electronegative, therefore oxygen will have the negative oxidation number of -2. So to work this out, chromium plus 4 lots of oxygen, which is -2, is equals to -2, okay, based on rule number 4. So chromium should work out as -2 plus 8 plus 6. Okay, moving on, Hno2 is an acid. Not sure if that is familiar to you. Acid can be broken down into ions, H plus and NO2 minus. So it's best that you work with 2 elements at a time. Okay, it's easier than working with 3 elements, hydrogen, nitrogen, and oxygen. So hydrogen can be eliminated because it following rule number 7, hydrogen is always +1. Between nitrogen and oxygen, oxygen is more electronegative, therefore it is -2. Based on rule number 4, the sum of the oxidation number in NO2 minus should equals to -1. 2 lots of oxygen atom is -2. Okay, so that gives us nitrogen to have an oxidation number of 3 +3. Yep. Okay, so I know I'm going really fast, but if you need to just stop or work it out at one point, just pause the video. Okay, HNO3 is also an acid, so I will break it down into its ions, H plus and NO3 minus. So notice that this is a nitrite and this is a nitrate. That's the old name. Okay, the new name is nitrate 3, and this will be nitrate something else, okay, which is something that we're going to work out after this, all right? So it's the Roman numerals, the Roman number that we add in formula. Okay, back to HNO3, hydrogen will by default have an oxidation number of +1. Oxygen will have an oxidation number of -2. Rule number 4 says that the sum nitrogen plus 3 lots of oxygen is equals to -1. So nitrogen would be -1 plus 6 plus 5. Okay, so the old name for this HNO2 is nitrous acid. So please include this if you have space. Well, you don't have space on your notes. You would have to do this on a foolscap paper. HNO3 is called the nitric acid, but now they are both called nitric acid. The only thing that separates them is the oxidation number. Okay, so in HNO2, the nitrogen is +3, so we call this nitric 3 acid. Okay, the number 3 in Roman. The other acid, which is HNO3, is also called nitric acid, but it's nitric V acid. Okay, so V stands for 5 in Roman numerals. So please take note of this new and old way of naming. Will they still accept nitrous acid, nitric acid? Yes, but to be safe, use the latest way or system of naming this acids that have different oxidation numbers. Okay, so the number in the numeral follows the oxidation state of nitrogen only. Next, ammonia NH3. Hydrogen will always be +1. And then you work out your nitrogen, 3 times +1. Rule number 4 says that the total will be, rule number 3, rule number 2. Okay, hydrogen having an oxidation state of +1 is rule number 7. Okay, next, CrH2O6 3+. Okay, it looks like there's a lot of things happening here. What can you do here? Now, H2O follows rule number 2. Sum of the oxidation numbers of the elements in a neutral compound is 0. That means H2O will be 0. Okay, so if I do that first, Cr and then +6, 0 is equals to +3. Chromium will have an oxidation number of +3. That's one way. I feel like that's the quickest way to work around it. Okay. H2O, you can treat it separately because they are like a separate entity. If you notice that they are being put in a bracket, so that means H2O is independent of the, it's not affecting the chromium. Okay, so you can treat H2O on the side. Again, following rule number 2, H2O should be equals to 0, and hydrogen will be +1. oxygen will be -2. Okay, so there's no competition there because hydrogen follows rule number 7, which is always +1. Oxygen follows rule number 9, which is -2. Cr2O72 minus, the priority given here would be of oxygen, so oxygen will be -2. Rule number 4 says that if we add up all the oxidation number of all the atoms in Cr2O72 minus, which is your dichromate ion, you should get the sum to be equals to the charge. So 7 times by -2, which is the oxidation number of oxygen, is equals to -2. So just to remind you, where I got that -2 as the sum or as the total is coming from the charge. So chromium is equals to -2 plus 14. Okay, so I have to work that out first, which is which is 12, correct? And chromium is 12 over 2 divided by 2 plus 6. Okay, don't forget there are 2 atoms of chromium in that formula. So chromium would be +6. Okay, do we still have a lot more? Potassium dichromate is the same. Try breaking this down into K plus and Cr2O7 2 minus. Okay, so I will let you work that out for yourself. Again, sodium hydroxide Na plus OH minus. Potassium manganate K plus MnO4 minus. So you work it out. So most of these ions are easily easily to be handled with because it just contains a monoatomic, and so it follows the charge. So for potassium, it will be +1, sodium, it will be +1, and potassium, it will be +1. Between chromium and oxygen, there's no problem. Oxygen will be -2. Chromium will work out to be +6, which is the same dichromate ion just now that we looked at the previous question. Yeah, Cr2O72 minus. So oxidation numbers should be the same. This one. Okay. Sodium hydroxide, oxygen will be -2, hydrogen will be +1, no problem there. The sum should be equal to -1. Potassium manganate, manganese and oxygen will not fight. Oxygen will have its negative oxidation number. Manganese will just follow whatever that's left for him. So that means it's -1 plus 8. So that's +7. Okay. So hopefully when you over time, you can work out the oxidation number without doing the working, but it has to be the correct calculation. Okay, so you will learn that it can be done in your head. Okay, it's not impossible. Okay, next we are going to look at the naming of compounds. I'm not sure if this is in your notes. Okay, so this is not in your notes. If you can just add this to your foolscap paper. The oxidation state of an element in a compound can be indicated by a Roman number. Iron 2 sulfate means that iron has an oxidation state of +2. Manganese, that is number 4, right? IV. Manganese 4 oxide means the manganese has an oxidation state of +4. So just like your nitric acid just now, nitric 3 acid and nitric 5 acid, the number in Roman numerals indicate the oxidation state of a particular element, okay? Not the whole formula, just a particular element. All right, so that's the example that I was talking about just now. Next, we're going to explain and use the terms redox. the term oxidation, reduction, and disproportionation in terms of electron transfer and changes in oxidation number. Okay, so I am sure you have all come across redox in O level, and then you learn terms like oil rig, oxidation is loss, reduction is gain. What else? You also learned oxidation in terms of losing or gaining oxygen or hydrogen. Okay, the only thing I think that would add on to what you already know is in terms of oxidation state, right? Explain and use the terms oxidizing agent and reducing agent. An oxidizing agent is a person who oxidizes another person, okay, or another species. Right, so there is a lot of things here which you don't have, but you can always add this on. I'm just giving you specific examples, all right? But you can just add on the main point, okay? So I'll talk about that later on. So what we have here, now redox is actually a combination of reduction and oxygen, okay? Sorry, reduction and oxidation. So oxidation is the process of electron loss. I think this is something that you are all familiar with. So if oxidation is loss of electron, reduction would be gain. Okay, yes, okay, correct, right? There is another, before I move on to that, now how do we know that electron is lost? You see that in a half equation, this is a half equation where it is not showing you the full reaction. So you see here, your zinc is converted into zinc 2+, but it doesn't tell us what zinc is reacting with. So this is a half equation, okay? So zinc will be converted into zinc 2+ to give out, to produce electrons. That means we have lost the electrons. So this is one way of identifying your oxidation or reduction is by looking at the position of your electrons. Whereas reduction is the gain in electrons. That means you add electrons. Your electrons is on the left side, okay? Chlorine takes up electrons to form chloride ion. So that's how you see it, okay? So I don't know if you are familiar with this already. Electrons is usually, oxidation is when you see your electrons on the right side, on the product side. Whereas reduction is when you see your electrons on the left side, which is on the reactant side. Okay, that's one way of looking at oxidation in terms of, sorry, I'll just highlight, in terms of electron, whether you lose or you gain. Okay, so that's number one. The next one of looking at oxidation state. If your oxidation state or oxidation number increases, then that reaction is an oxidation process. Okay, so this is probably new for you. Likewise, if it decreases, then that reaction is a reduction reaction or reduction process. Okay, so if we just quickly look at working out the oxidation number, zinc is a neutral atom, so zinc would be 0. Zinc 2+ is a monoatomic ion. Following rule number 3, it has the oxidation number as its charge. So you can see that zinc goes from 0 to +2. That is an increase in oxidation number. So it's an oxidation process. For reduction, chlorine, this follows rule number 1, all uncombined elements, because there's only one type of elements in Cl2. So both atoms will have an oxidation number of 0. Okay. Now I'm only talking about one atom here per atom. Okay. Chloride ion follows rule number 3, where the oxidation number is the same as the charge on the chloride ion. that's -1, right? But don't forget, I have 2 lots of chloride ion, so I have to multiply it by 2. But the change in oxidation, I can either look it as from 0 to -1 per chlorine atom or per ion, or from 0 to -2 for 2 chlorine atoms. It doesn't matter because it is still a decrease. Whether you count it for 1 chlorine atom or 2 chlorine atom, the number will still decrease. Okay, it goes from 0 to a negative number. So that's how you know reduction. The third way of looking or spotting your oxidation reduction is by oxygen. Okay, whether you have lost or you have gained oxygen. Okay, so here it's not easy to see, but you can see that the copper becomes CuO. So that means copper has gained an oxygen and therefore it is oxidized. Whereas in the other equation, H2O, it goes from H2O to become H2. You have lost the oxygen. So we say that the oxygen has been reduced. Okay, so it's not as easy to see in terms of oxygen and hydrogen because there are a lot of oxygen and there are a lot of hydrogen as well in an equation. Okay, the easiest way to spot them is by working out the oxidation number or looking at the electrons, but you only see electrons in half equations. This is the full equation. You see the copper reacting with water, H2O, to form copper oxide and hydrogen gas. Now you don't see the electrons here. So this is also difficult if you want to spot whether you have gain or lose electrons. So the easiest way I would say would be using oxidation number. So you really have to be good at working out the oxidation number of each element in each molecule or in each formula. Okay. The next thing is by looking at, so the third way of looking at redox is by spotting the oxygen, whether you have gained or lost it. And the last one is by looking at hydrogen, whether you have gained or lost hydrogen. So I'm just going to show that in oxidation, hydrogen will be lost. So it's the opposite to oxygen. Oxygen, you gain for oxidation. Hydrogen, you lose for oxidation. Electrons, you lose for oxidation. Okay, so in a way, hydrogen and electrons have the same relationship. Okay, when you gain hydrogen or electrons, it's a reduction. When you lose hydrogen or electrons, it's an oxidation. Okay, moving on. Redox equations and half equations. So redox reactions are reactions in which oxidation and reduction take place together. In a reaction, you must always have reduction and oxidation together. You cannot just have reduction alone. If you have reduction alone, then that's not a reaction yet. That is a half equation. Okay. While one species is oxidizing, another is reducing. Okay, and in redox reaction is made up of two half equations. The first half equation is of oxidation and the second half equation is the reduction. So you have to be able to identify what's the difference between a redox equation and half equations. So we'll look at the next slide, and this is in your notes on page 2. All right, so you have an equation here. This is called an ionic equation. It is a full, complete Ionic equation, you've got reactants and you've got products. Okay, a full equation, a full redox equation is made up of reduction reaction, which is going from bromine into bromide. That is your half equation for reduction. Going from iodine to, going from iodide to iodine, that is your half equation for oxidation. Okay, so I will show you bromine to bromide. I'll use the same highlighter. That is your reduction. And then iodide to iodine. I don't know if you can see this. Okay, that is your oxidation. Okay, so you can always do the reverse. All right, you combine half equations together to get a full equation, or from a full equation you get a half equations. In this case, we're doing the reverse. From the full equation, full redox, we are breaking it down into oxidation, half equation for reduction and half equation for oxidation. Now you notice that in your, you've only taken bromine, Br2, and bromide. Bromine and bromide, okay? Then you suddenly have these electrons. So I will teach you later on why these electrons is suddenly here, okay? The reason for this is, of course, there's no other reason except to balance your half equation. Even though it's half an equation, it also needs to be balanced, okay? Balance in atoms, balance in charge, especially important because that's something that we tend to overlook at. For your whole equation, your complete equation, you also have to balance your charge, okay? So whatever equation, as long as it's an equation still, whether it's half or full, you always need to balance the atoms and the charges, okay? So you look here, the electrons is on the left side. So that's the easiest way to spot whether bromine has undergone reduction or oxidation. Okay, if you don't like that, I would look at the oxidation number. Bromine has an oxidation number of, 0, because it's a neutral compound. Bromide has an oxidation number of -1, and because there are 2 of them, you just multiply it by 2. So you go from 0 to -2, that's a reduction. Your oxidation number has decreased. It goes from 0 to -2. Whereas for oxidation, should have used a different color just now. Otherwise, I don't want to confuse you. So this one, I'll change it to pink. And then for oxidation, I'll use blue. So iodide ion, I-1, has an oxidation number of -1. It's the same as its charge. And there are 2 lots of this. So I'll just multiply it by 2. Iodine in I2, okay, is 0. So I go from -2 to 0. That is an increase in oxidation number. So it's an oxidation process. So I will just write this down. Oxidation number has gone up. And for reduction, oxidation number has gone down. Okay. Next is okay. Right, so I've talked about this. The electrons are on the left for reduction. For oxidation, the electrons are on the right. So you notice that there are 2 electrons, right? I'll teach you how to balance that later. Another thing that I want to talk about is the oxidizing agents and the reducing agents, okay? So if bromine is reduced to bromide, we say that iodide is the reducing agent. Okay, sorry. Iodide reduces bromine into bromide. Okay, so that makes iodide reducing agent. Who is the oxidizing agent? Okay, so look at the person who is being oxidized. Pink. Iodide is being oxidized to iodine. Okay, I don't know how to, there's no space. Maybe I'll do it outside. Iodide is being oxidized to iodine, and this is called an oxidation process. Okay, if iodine is being oxidized, that means bromine is the oxidizing agent. Okay, so I repeat, bromine oxidizes iodide into iodine. Now, at the same time, bromine is also being reduced. Iodide, who is the reducing agent, is also being oxidized. Okay, so actually, your oxidizing agents will oxidize other species, but itself will be reduced. Okay, for reducing agents, it reduces another species and itself gets oxidized. So it does things to other people, itself also changes. Okay. In terms of in terms of electron transfers, we know that our bromine is an oxidizing agent, right? And it takes in the electrons. So we say that bromine accepts electrons to form bromide. Reducing agents in general are electron donors. Your reducing agent is iodide, and iodide is being oxidized into iodine to donate electrons. Confused yet? Just bear with me. Bromine is an oxidizing agent that gets reduced. Oxidizing agent that gets itself reduced. Iodide is a reducing agent. Reducing agent that gets itself oxidized. So if you want if you're wondering where this electron acceptors, electron donors are coming from and how we define them, it comes from the electrons there. Okay. Electron left, electron on the left side, you accept, electron on the right side, you donate. When naming oxidizing and reducing agents, always refer to full name of substance and not just the name of the element. So in this case, there's no example for this, but you just have to be specific with who your oxidizing agent or reducing agent is. Okay, so that's the point of that message. Okay, so we've identified this earlier on just now. The oxidizing agent is bromine water. Bromine water is Br2 aqueous. It is an electron acceptor. The reducing agent is the iodide ion. You have to be careful. If you say iodine, it's wrong. Okay, iodine is I2. It has to be iodide ion. There are two types of iodine species here, and you have to be very specific. Okay, if you just write down I, which I is it? Is it iodide or is it iodine? An oxidizing agent, sometimes called oxidant, okay, is the species that causes another element to oxidize with itself being reduced. So this is what I was talking about. A reducing agent or a reductant is the species that causes another element to reduce, but itself gets oxidized in the reaction. Okay, so it's like you change other people, there's a consequences to yourself. You oxidize other people, yourself will be reduced. And it has to be the opposite. You cannot oxidize other people and then yourself is being oxidized as well. It has to go in the opposite reaction. Okay. Looking at the oxidation numbers, I've talked about this already. How have I been able to identify whether it's a reduction or an oxidation? It is because you look at the change in oxidation numbers of each of the species. Okay, electrons, there's no oxidation number or oxidation state for electrons, so you just leave it out of the way. Okay, some substances can act as both oxidizing and reducing agents in different reactions. Make sure you know that they are behaving in different reactions. Okay, it cannot be behaving as oxidizing agent and reducing agent in the same reaction. Okay, what do I mean by this? Their nature is dependent upon what they are reacting with in the reaction condition. So here is an example where H2O2 can behave as an oxidizing agent and reducing agent at different reaction depending on the species that it reacts with. Okay. First example, you can copy this down, add on to your notes, right? Sorry, excuse me. When H2O2 reacts with Fe2+, it acts as an oxidizing agent. How do we know that? Because itself is being reduced. Okay, so I've worked out the oxidation number. So if you look at H2O2, the oxygen, okay, goes from -1 to -2. So that is a decrease. Okay, be careful with your negative numbers. I should point this out. Oxidation number of oxygen. Okay, oxygen is -1. Hydrogen is the same as +1. So you go from -1 to -2. That is a reduction because oxidation number decreases. Okay, iron, you go from Fe +2 to +3. That is an increase. That's an obvious increase. Oxidation number increases. Therefore, it is an oxidation. Right? Next is you just have to identify your reducing and oxidizing agent. I like to go the opposite way. Okay, so if Fe2 plus is being oxidized, Fe2 plus must be the reducing agent. Okay, so you just follow the opposite. Itself is being oxidized, so it acts as a reducing agent or a reductant. Whereas H2O2 is being reduced, therefore H2O2 is an oxidizing agent. Okay, so but my focus is I forgot about this example. Actually, I was trying to show you H2O2 acting as an oxidizing agent. Okay, when it reacts in a different reaction with a different species, this time I'm using Fe3 plus. Okay, so Fe3 plus, my H2O2 plus some hydroxide. So this has to be in an alkaline condition. Okay, so now my product of H2O2 is no longer H2O. There's H2O in there, but that's not from the H2O2. I'm going to use, wait, oxidation is green. Okay, so I go from -0 of my oxygen in H2O2, same thing, to 0 in O2. So I just write down O, okay? So -1 to 0 is an increase. Therefore, it is oxidation. Okay, so because H2O2 is now being oxidized, it acts as a reducing agent. Just follow the opposite. Okay, oxidation, it's a reducing agent. Reduction, it's an oxidizing agent. So this is an example where one species can behave as an oxidizing agent in one reaction, and then it behaves as a reducing agent in another reaction, right? Okay, for example 2, I want you to identify, okay, in each of the following equations, state which reactant has been oxidized and which has been reduced. Okay, so I will stop here and leave you to do example 2, because if I continue on with the next part, it will be, I think it will be long. Okay, so we'll stop here and please try to do example 2. Okay, and then you answer it on your notes, and then later on I will ask you to write down the answers on forms, and then you can just mark it yourself. Check whether you have gotten the correct answer or not. Okay, as usual, the link to the questions on forms will be in the description box. Okay, Assalamualaikum, and thank you everyone.